Electroflow power quality conditioning systems make several claims. Firstly, the system regulates voltage. Secondly, it keeps all three phases in balance. Thirdly, the system mitigates harmonics. Fourthly, Electroflow suppresses transients. And fifthly, it improves power factor to above 95%. Regarding opinions, there are both positive and negative viewpoints to consider. On the positive side, Electroflow claims to significantly improve power quality by addressing various issues, such as voltage fluctuations, phase imbalances, harmonics, and transients. This can potentially lead to reduced equipment failures, increased efficiency, and improved product quality. Additionally, by regulating voltage and improving power factor, Electroflow may help reduce energy consumption, resulting in lower utility bills. Some users also report that Electroflow helps facilities meet power quality standards set by regulatory agencies or industry best practices. Finally, many users have expressed satisfaction with the performance and reliability of Electroflow systems. However, there are also negative opinions to consider. Electroflow systems can be expensive to purchase and install, making it an investment that may not be feasible for all businesses. Furthermore, Electroflow systems are not suitable for all power quality issues. It is important to assess the specific needs of your facility before making a decision. Electroflow systems require regular maintenance and monitoring to ensure optimal performance, which can add to the ongoing costs of ownership. While some users report positive results, there is limited independent scientific data to fully validate the claims made by Electroflow. In conclusion, Electroflow power quality conditioning systems can potentially provide benefits such as improved power quality, reduced energy consumption, and compliance with standards. However, it is important to carefully consider the cost, suitability, and maintenance requirements before making a decision. Independent verification of the claimed benefits may be necessary to determine the effectiveness for a specific application. Power quality refers to the maintenance of a steady voltage level, stable frequency, and clean sinusoidal waveform. Power quality issues can manifest as voltage sags, voltage swells, harmonics, transients, and frequency variations, each of which can disrupt the operation of sensitive electronic equipment. Voltage sags are short-term reductions in voltage, typically lasting from a half cycle to a few seconds. They can be caused by starting large motors or by faults in the power system. Voltage swells are short-term increases in voltage, also lasting from a half cycle to a few seconds. They can be caused by sudden load reductions or by switching off large capacitor banks. Harmonics are distortion of the voltage or current waveform caused by nonlinear loads such as variable frequency drives, electronic ballasts, and computers. Harmonics can cause overheating of equipment, increased losses in transformers and conductors, and interference with communication systems. Transients are very short duration, high amplitude surges in voltage or current. They can be caused by lightning strikes, switching operations, or electrostatic discharge. Frequency variations are deviations of the power system frequency from its nominal value, typically 50 Hz or 60 Hz. Large frequency variations can cause equipment to malfunction or shut down. Power quality problems can have a significant impact on businesses and industries, leading to equipment damage, production downtime, and financial losses. The cost of poor power quality can be substantial, especially for industries that rely on sensitive electronic equipment. There are various methods for improving power quality, including installing surge suppressors, uninterruptible power supplies, harmonic filters, and voltage regulators. Surge suppressors protect equipment from voltage transients by diverting excess energy to ground. Uninterruptible power supplies provide backup power in the event of a voltage sag or outage, ensuring that critical equipment continues to operate. Harmonic filters reduce the level of harmonics in the power system, preventing equipment overheating and other problems. Voltage regulators maintain a constant voltage level, compensating for voltage sags and swells. When evaluating a power quality conditioning system like Electroflow, several factors should be considered. Firstly, perform a power quality audit to identify the specific problems affecting the facility. This involves measuring voltage, current, harmonics, and transients to determine the extent and nature of the issues. Secondly, assess the suitability of the Electroflow system for addressing the identified power quality problems. Consider the system's capabilities in terms of voltage regulation, harmonic mitigation, transient suppression, and power factor correction. Thirdly, evaluate the cost-effectiveness of the Electroflow system, taking into account the purchase price, installation costs, and ongoing maintenance expenses. Compare the cost of the system to the potential benefits in terms of reduced equipment failures, increased efficiency, and energy savings. Fourthly, research the reputation and experience of the manufacturer. Look for customer reviews and testimonials to get an idea of the system's performance and reliability. Fifthly, request a demonstration of the Electroflow system to see how it performs under real-world conditions. This will help to evaluate its effectiveness in addressing the specific power quality problems at the facility. Sixthly, obtain independent verification of the claimed benefits of the Electroflow system. This may involve conducting independent testing or consulting with power quality experts. Power factor is a measure of how effectively electrical power is being used. It is defined as the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amperes. A power factor of 1.0 indicates that all of the electrical power is being used effectively, while a power factor of less than 1.0 indicates that some of the power is being wasted. Low power factor can result in increased energy costs, reduced equipment capacity, and voltage drops. Utilities often charge a penalty for low power factor as it increases the load in the power system. There are several methods for improving power factor, including installing power factor correction capacitors, using synchronous motors, and replacing inefficient equipment. Power factor correction capacitors provide reactive power, which offsets the reactive power drawn by inductive loads such as motors and transformers. Synchronous motors can be operated at a leading power factor, which helps to improve the overall power factor of the system. Replacing inefficient equipment with high-efficiency equipment can also help to improve power factor by reducing the amount of reactive power drawn. Harmonic mitigation involves reducing the level of harmonics in the power system. Harmonics can be caused by nonlinear loads such as variable frequency drives, electronic ballasts, and computers. Harmonic distortion can cause a variety of problems, including equipment overheating, increased losses in transformers and conductors, and interference with communication systems. There are several methods for mitigating harmonics, including installing harmonic filters, using harmonic reducing transformers, and implementing active harmonic cancellation. Harmonic filters are designed to absorb harmonic currents, preventing them from propagating through the power system. Harmonic reducing transformers are designed to reduce the level of harmonics generated by nonlinear loads. Active harmonic cancellation involves using electronic devices to inject harmonic currents that are equal and opposite to the harmonic currents generated by nonlinear loads, effectively cancelling them out. Transients are very short duration, high amplitude surges in voltage or current. They can be caused by lightning strikes, switching operations, or electrostatic discharge. Transients can damage sensitive electronic equipment, causing it to malfunction or fail. Surge suppressors are designed to protect equipment from voltage transients by diverting excess energy to ground. Surge suppressors typically use metal oxide varistors, also known as MOVs, to clamp the voltage to a safe level. Uninterruptible power supplies, or UPS, provide backup power in the event of a voltage sag or outage. UP systems typically use batteries to store energy, which can be used to power critical equipment for a limited time. There are several different types of UP systems, including standby UPS, line interactive UPS, and online UPS. Standby UP systems switch to battery power when a voltage sag or outage is detected. Line interactive UP systems regulate the voltage to maintain a stable output voltage. Online UP systems continuously supply power from the battery, providing the highest level of protection against power quality problems. When selecting a power quality conditioning system, it is important to consider the specific needs of the facility. A power quality audit can help to identify the types of power quality problems that are present in the equipment that is most vulnerable. The system should be capable of addressing the identified power quality problems and protecting the sensitive equipment. It is also important to consider the cost-effectiveness of the system, taking into account the purchase price, installation costs, and ongoing maintenance expenses. Additionally, be sure to evaluate the reputation and experience of the manufacturer and seek independent verification of the claimed benefits of the system. Power quality disturbances can be classified into several categories according to IEEE Standard 1159. This standard defines the characteristics of various power quality phenomena, including transients, short-duration voltage variations, long-duration voltage variations, voltage imbalance, waveform distortion, and frequency variations. Transients are momentary voltage or current spikes that can occur due to lightning strikes, switching operations, or electrostatic discharge. They are characterized by their short duration and high amplitude. Short-duration voltage variations include voltage sags, voltage swells, and interruptions. Voltage sags are short-term reductions in voltage, typically lasting from a half cycle to a few seconds. Voltage swells are short-term increases in voltage, also lasting from a half cycle to a few seconds. Interruptions are complete losses of voltage, lasting from a few cycles to several seconds or longer. Long-duration voltage variations include undervoltages and overvoltages. Undervoltages are reductions in voltage that last for more than a few seconds. Overvoltages are increases in voltage that last for more than a few seconds. Voltage imbalance, also known as voltage imbalance, occurs when the voltages in the three phases of a three-phase power system are not equal in magnitude or phase angle. Voltage imbalance can cause increased losses in motors and transformers, as well as equipment malfunction. Waveform distortion refers to deviations from the ideal sinusoidal waveform. Common types of waveform distortion include harmonics, notching, and noise. Harmonics are sinusoidal voltages or currents with frequencies that are integer multiples of the fundamental frequency. Notching is a periodic voltage disturbance caused by the commutation of power electronic devices. Noise is unwanted electrical signals that can interfere with the operation of sensitive equipment. Frequency variations are deviations of the power system frequency from its nominal value, typically 50 Hz or 60 Hz. Frequency variations can cause equipment to malfunction or shut down. Power quality monitoring is the process of measuring and analyzing power quality parameters to identify and diagnose power quality problems. Power quality monitoring can be performed using portable power quality analyzers or permanently installed power quality monitoring systems. Power quality analyzers typically measure voltage, current, harmonics, transients, and other power quality parameters. Power quality monitoring systems can provide continuous monitoring and alarming of power quality parameters, allowing for early detection of power quality problems. The information collected during power quality monitoring can be used to identify the root causes of power quality problems and to develop solutions to mitigate them. Power quality standards and guidelines provide recommendations for maintaining good power quality. These standards and guidelines cover a wide range of topics, including voltage regulation, harmonic limits, transient protection, and grounding. Some of the most widely recognized power quality standards include IEEE Standard 519, which provides recommendations for harmonic control in electrical power systems, and IEEE Standard 1100, which provides recommendations for powering and grounding sensitive electronic equipment. Compliance with power quality standards and guidelines can help to ensure that electrical equipment operates reliably and efficiently and can minimize the risk of equipment damage and downtime. Power quality is an important consideration for businesses and industries that rely on sensitive electronic equipment. By understanding the causes and effects of power quality problems, and by implementing appropriate power quality solutions, organizations can protect their equipment, improve their productivity, and reduce their energy costs. The specific power quality requirements of a facility will depend on the type of equipment being used and the sensitivity of that equipment to power quality disturbances. A power quality audit can help to identify the specific power quality needs of a facility and to develop a plan for addressing those needs. Power quality solutions can range from simple surge suppressors to complex harmonic filters and voltage regulators. The choice of power quality solution will depend on the nature and severity of the power quality problems being addressed, as well as the cost and performance requirements of the system. In addition to addressing power quality problems at the facility level, it is also important to work with the utility to ensure that the power system provides a reliable and high-quality power supply. Utilities have a responsibility to maintain the power system and to address power quality problems that may originate on the grid. By working together, facilities and utilities can ensure that the electrical equipment operates reliably and efficiently, and that power quality problems are minimized. Evaluating power quality solutions requires a systematic approach. Firstly, define the scope of the evaluation, including the specific power quality problems that need to be addressed and the equipment that needs to be protected. Secondly, gather data on the power quality performance of the existing system, including measurements of voltage, current, harmonics, transients, and other power quality parameters. Thirdly, identify potential power quality solutions that can address the identified problems, considering factors such as cost, performance, and reliability. Fourthly, evaluate the potential power quality solutions using a combination of modeling, simulation, and testing. Fifthly, select the power quality solution that best meets the needs of the facility, considering factors such as cost effectiveness, performance, and reliability. Sixthly, implement the power quality solution and monitor its performance to ensure that it is effectively addressing the identified power quality problems. When evaluating the cost effectiveness of power quality solutions, it is important to consider both the direct costs such as the purchase price and installation costs, and the indirect costs such as the cost of downtime, equipment damage, and lost productivity. A comprehensive cost-benefit analysis can help to determine whether the benefits of a power quality solution outweigh the costs.